Hello again, physics friends. Today we are going to talk about the so-called equation of the orbit for central forces. So if you recall, in the past we've shown that for a two-body central force system, we can write down the equation of motion for the r coordinate as mu r double dot is equal to the derivative with respect to r of some effective potential, where that effective potential contains two terms. One is the actual potential associated with the central force, that's U of r, and the other is this 1 over r squared term that involves the angular momentum. So there's a radial piece and an angular piece in the effective potential. This angular momentum, in turn, is defined in terms of the r and phi coordinates as mu r squared phi dot. So this is the angular momentum of the system. Today, though, so this equation of motion here is a second order differential equation in time. So this is d squared r dt squared. And if you solve it, in principle, you can find r of t, the position as a function of time, or the separation between the two objects as a function of time. Okay? And sometimes we need that or want that in a given problem, but sometimes we're just interested in the shape of the orbit. For example, for a planetary orbit around a star, we would expect an ellipse, an elliptical orbit. We might not care where the planet is at any given time on the ellipse, but we might just want to know, is the orbit an elliptical orbit, or is it circular, or is it hyperbola, or is it some other geometry? We just might want to know the shape of the orbit. For the shape of the orbit, we don't need r of t. If we care about the shape of the orbit, we actually want r as a function of phi, right? How far away are the objects as a function of the angle? And that describes the geometry, and it doesn't worry about the time component. So what we're going to do today is reformulate this equation of motion from a equation of motion in time to one that involves derivatives with respect to phi. So we want to take time derivatives and make them derivatives with respect to this angle, so that we'll have an equation of motion, or a differential equation with derivatives with respect to phi. Okay, so that's where we're heading today. So the first thing I'm going to do is I'm going to write this equation out, but I'm going to actually take the derivatives of u effective, and we're going to therefore get a 1 over r cubed term, and then we'll get a minus du dr, which is the force. So when we take that, when we write that equation out, we'll have mu r double dot is equal to L naught squared over mu r cubed, and then added to that is the central force F of r. So this is going to be our starting point for today. We're going to make use of two mathematical techniques today. Okay. The first, which I'll call A, is that we're going to redefine r. We're going to use a new variable, u, which is defined to be 1 over r. Now be careful. I'm going to use capital U like this as the potential. And I'm going to use this lowercase u as a new variable, a renaming of the position variable, but it's inverse of the radial coordinate r. Okay. The second is that we're going to use the chain rule to reformulate d dt as d d phi. And specifically what we're going to find is that d dt is equal to L naught u squared over mu d d phi. And we'll work out why that is in a minute. Once we have those two conversions, we're going to apply them to this time differential equation and convert it into a differential equation with respect to angle. So our first task is to show why it's true that a time derivative d dt is given by d d phi, but with this prefactor. So let's see why that is. We have a few steps for this derivation, and we're going to say using the chain rule, we can write d dt as d d phi, but with a d phi dt up front. Right? So this is the chain rule. If d phi dt, d d phi is the same thing as the time derivative d dt. d d phi is nothing but phi dot. Okay, and now we know an expression for phi dot in terms of r and mu and rho squared, so we're going to apply that here. So we'll replace phi dot with L naught over mu r squared. And then we're going to make one more substitution, which is in place of 1 over r, we're going to replace that with u. And here we have a 1 over r squared, so we're going to get a u squared. Okay, and then we're done. So we're going to hang on to this for a moment, and we're going to make use of it when we convert this differential equation into a differential equation with respect to phi. Okay, so now we're going to make use of it. We need an r double dot. So let's take this in turn. Let's start with r dot and then go from there. So we have r dot is equal to d dt of r, the time derivative of r, but we have an expression now for d dt, and that expression is L naught u squared over mu d d phi. Okay. Now, r itself, remember, is a 1 over u, so I'm going to apply that here. And now we need to take d d phi of 1 over u. Well, the derivative of 1 over the function would be minus 1 over the function squared times du d phi. So we have L naught u squared over mu, that piece out front stays as it is, and then we have a minus 1 over u squared du d phi, like so. So at the end of the day, we have an expression for r dot. We get this nice cancellation of these u squareds. We get minus L naught over mu, two constants, times du d phi. So that's step 1. Okay. Step 2 is to say r double dot is d dt of r dot, okay, which is d dt of the thing we just found. Okay, so these constants come out, minus L naught over mu. And once again, we're going to use our expression for d dt, like so. And so now when all is said and done, we are going to have r double dot is equal to minus L naught squared over mu squared, u squared, and then second derivative of u with respect to the angle phi. Okay, so we've now converted a second derivative in time to a second derivative in angle, and we pick up these factors out front. So we can now take this result right back into our equation of motion for r, and this deals with the right-hand side here. We're going to replace the r double dot with this new expression. And we can use the notation of double prime. We can say u double prime of phi is just defined to be the second derivative of u with respect to phi. So the tick primes refer to derivatives with respect to angle, and the two dots refer to derivatives with respect to time. So when we come back to this equation and we make these substitutions, we are going to find we have mu times r double dot, which is minus L naught squared over mu squared, u double prime. That's our left-hand side. And our right-hand side will be L naught squared over mu u cubed plus F, the force F. Okay, so we have some simplification that we can make. We'll lose one factor of mu, and we can divide through by u squared. Like this. And at the end of the day then, and we can divide through by those constants as well. So at the end of the day, we'll have u double prime is given by minus u of phi minus mu over L naught squared u squared with an F in the numerator. So this is our new equation to find the shape of the orbit. The shape of the orbit, again, being the separation r as a function of angle. So first, the differential equation we'll solve mathematically will give us u as a function of angle, but u is simply 1 over r. So once we know u, we know r as a function of angle. Okay, so we have these two main results. We'll clean up the screen a little bit. We have the original differential equation, and we've defined what our L naught angular momentum is. We've reformulated that differential equation in time to a differential equation with respect to angle, where, remember, u double prime is defined to be the second derivative of u with respect to angle. And now this applies for any central force, not just gravity, but any force at all. So what we want to do next is a couple examples, right? And each example will have a different force. We'll put in the force, we'll solve the differential equation, and we'll try to understand the shape of the resulting orbits, r of phi. So what two examples should we use? Well, as our first one, we'll use a free particle. And by free particle, I mean the interaction force between the two particles is 0, therefore we would expect straight line motion. Okay. Number 2, we'll look at the gravitational force. And in the gravitational force, we have an attractive force, so the force is negative, points towards the origin. And that force is proportional to 1 over the separation squared. Okay, so in our first example, we're going to turn off the force. We start with our equation of motion in terms of phi. We turn off that second term on the right-hand side, and we're left with a differential equation. Second derivative of u is equal to minus u. Well, by now, we've seen that form of an equation over and over and over again. That is the mass on a spring, simple harmonic motion, with a resonant frequency omega squared of 1, right? Remember, x double dot equals minus something times x. That something is omega squared. So right away, we know that this u of phi has got to be a periodic function, specifically a sinusoidal or cosinusoidal function, and we know that we can write this in many different ways, but one is a cosine with an amplitude and a phase. And we can write it like this, cosine omega phi minus a phase delta. And a and phi depend on initial conditions. Here omega is 1, so we can simplify this to just a cosine of phi minus delta. That's our u of phi. Now we know that r of phi, which is what we seek, is 1 divided by u of phi. And again, just to reiterate, this u is not the potential. This u is just our variable, a redefinition of the radial coordinate r. It's the inverse of that radial coordinate r. So we have 1 over a cosine of phi minus delta. Okay. And what is this 1 over a? Well, 1 over a is, if you think about this r phi, if we put in an angle phi that's equal to delta, then we'll have cosine of 0, that's 1. So this 1 over a corresponds to r at phi equals delta, right? So we see that r for for phi equal to delta is equal to 1 over a cosine of delta minus delta. That's 1 over a times cosine of 0, which is 1. So this 1 over a we can just rename to r naught, where r naught corresponds to the radial coordinate for a given angle phi equal to delta. So if you'd like, we can make a plot here. Maybe this is our xy plane, and we can say there's some separation from the origin r naught that applies when the angle phi is equal to delta. That's a point. That point is a point on our curve r of phi. So what is the shape of this curve, right? If I have my equation for the orbit is given by r of phi equals r naught divided by cosine of phi minus delta. What is the shape of this curve? So I want to come back to this equation and just rewrite it in a slightly different way. I'll say r naught is equal to r times the cosine of phi minus delta. So this is making me think of like trig functions and right triangles. If I have a hypotenuse r, then r naught will be the length of the side adjacent to the side to the angle phi minus delta. Okay. So I want to construct, this motivates me to construct a right triangle with hypotenuse r of phi. So if I think about this red dashed line perpendicular to the segment of length r naught, the hypotenuse would be opposite that right triangle, or that right angle rather. We'll call that r of phi. And the angle in here, this angle right here, needs to be phi minus delta. Okay, so that first angle was delta. And so if this is phi, oops, I wrote the wrong thing. I said delta and I wrote phi. That first angle is delta. If the second angle is phi, then this angle in here is phi minus delta. So I'm going to move my r naught a little bit over. This angle in here is phi minus delta. Okay, so I have a right triangle with hypotenuse r of phi. This side is r naught, and this angle is phi minus delta. And you can keep playing that game, right? I could make a new r. It would form a right triangle. It would have a new angle phi minus delta, and this equation will hold. So in fact, any point on this red line satisfies that purple equation. Okay. So surprisingly, perhaps, this is the equation of a straight line in polar coordinates. Okay. So my curve r of phi is a straight line. Now maybe that's not so surprising, because this is a situation that you expect when there's no force. If there's no interaction, the object should travel in a straight line. And indeed, that's what we see. Okay, for our second example, we're going to consider the gravitational force. So this is the force of gravity. We know gravity is a 1 over r squared force, and it's attractive, so we have a minus sign. And we know that we can write that gravitational force as minus gmm over r squared, where m1 and m2 are the masses of the objects involved. We don't want to have to write that over and over, so we're just going to call that constant gmm gamma. So our force is now minus gamma over r squared, or keeping in mind that we're going to be using this 1 over r variable little u, we'll call the force equal to minus gamma u squared. Okay, so now we come back to that equation for the shape of the orbit, u double prime with derivatives with respect to phi, And we make use of this here. So we have u double prime of phi equals minus u minus mu over L naught squared u squared times the force. And the force is minus gamma u squared. So that's kind of interesting. These u squareds cancel, minuses turn to pluses, and our differential equation looks like the following. Okay, so this is the same differential equation as last time, except we have an additional constant in the mix. And I've written a minus, but this really should be a plus on the constant term. So the fact that this last term is constant will be true for any force that's 1 over r squared, because that force would then be a u squared. The u squared from the force will cancel the u squared that's in the equation for the shape of the orbit, and you'll be left with a constant. Now, a simple way to get at this solution is to choose a new variable, we'll call it w, which is the same as u, except offset by a constant. And the constant that we'll use for the offset is minus the constant in our equation. Okay, and you'll soon see why that is. Well, the first derivative with respect to phi of w is equal to the first derivative with respect to phi of u, and the constant goes away. So the second derivative is then the second derivative of u. So the left-hand side of our equation will just be w per double prime, and then the right-hand side will combine these two terms in a way that gets rid of the constant. And so we are left with a w double prime phi is equal to minus w of phi. And once again, that's now the same equation of motion, the same structure that we saw in the first example, and the same as a mass on a spring. Second derivative is equal to minus the function. So we know that once again, the solution will be a periodic function, well, a subharmonic motion. So we can write this as an amplitude times the cosine of omega phi, but omega in this case is simply 1, as it was in the last example. So we can reuse that solution. Okay. So let's talk about this delta term a little bit. If we look back at our previous solution, delta was the angle from the x-axis out to this r naught line segment, okay, where r naught was 1 over a. But we could have chosen a new coordinate system that pointed parallel to r naught like this, if this was our x prime, and then our y prime would be tilted over there. In that case, that would give us delta of 0, right? Because now the angle between our x prime axis and the r naught segment is 0. So we can always choose a coordinate system to get rid of this delta term. So we're going to assume that we can do that here. So we'll choose delta of 0. And the other thing to point out is, remember, this 1 over a was like this r naught term, okay? And that's basically a distance from the origin, and that distance is going to be positive. So we just want to note that 1 over a, and therefore a, and note that a is a positive constant. So now we say w of phi is just a cosine phi. We've gotten rid of the delta. And if we know w, then we can find u, because u is w plus this constant. So the next step is to say, now I know what u is, plus gamma mu over L naught squared. Okay, so now I know what u is, and I can massage this a little bit for reasons that will become clear later. I'm going to factor out gamma mu over L naught squared, and I can write this as 1 plus some other constant times the cosine of phi, where in this case, this epsilon term is defined to be a L naught squared over gamma mu. And since this is all equal to u of phi, I can equivalently write it as 1 over r of phi. And the final step here is to create one more new constant. We'll call a new constant c equal to L squared over gamma mu. And that gets rid of this term here, or just simplifies it. So this whole term becomes a 1 over c, so that when we invert it to solve for r, we have r of phi is equal to c over 1 plus epsilon cosine of phi. Okay. And it turns out that this equation gives the Keplerian orbits for gravity, which could be ellipses or parabolas or hyperbolas. And in general, we call these conic sections. We call them conic sections for the following reason. If we come over to the bottom left corner, I've drawn a cone and I've drawn a plane slicing that cone. And one way to slice that cone is with the plane parallel to the base of the cone, in which case you get a circle. You could also slice with the plane at an angle relative to the base at a slight angle, and then you get an ellipse. If the plane were parallel to one of the generating lines of the cone, then you would generate a parabola like that, and steeper than that, you would generate a hyperbola like this. We're going to explore this in more detail when we talk about Keplerian orbits, specifically for gravity, and we'll dive into these bound orbits, the circles and ellipses, and we'll talk about unbound and marginally bound orbits, and we'll come back to these ideas of conic sections. So we're going to revisit this equation for the shape of the orbit again going forward. But in today's video, we were basically taking the equation of motion for the radial coordinate in a central force, reformulating it in terms, instead of being in terms of time derivatives, reformulating it in terms of derivatives with respect to angle, and then solving for radial coordinate as a function of angle, which tells us about the shape of an orbit. We found if there's no interaction between the two particles, then r as of a function of phi will be a line. If there is a 1 over r squared interaction between the particles, then we get these conic sections. And we'll describe in more detail the features of these conic sections in a future video. But for now, we're going to stop here. So take care, be well, and we'll see you next time.